So again, we have this meter stick, and it's connected as such. And we have a fixed pivot point on the left-hand side. That's where I was holding it. And there's a string attached to the right-hand side. We're going to cut it, and the instant it's cut, I'd like the angular acceleration of the meter stick. Now, I know that this is a conservation of energy unit, but sometimes the problems mix different things together. Energy is really good at telling us about height and velocity. Not so good when it comes to acceleration. What is something that's good at telling us about acceleration? Guys, we only have three major principles that you've learned this year. Unit 2, forces. Unit 3, energy. Unit 4, momentum. And they were repeated with Unit 5 and 6. So of those three, which one deals with acceleration? No. No, you had 3 tries. Bound to get it eventually. So yeah, it's a unit we just left, guys. Which one has net force equals MA? And which one has net torque equals I alpha? I mean, it's got to be the one that has A in the equation. So it's got to be a force equation or a torque equation. This one is torque. So I'm telling you where to start. This is a net torque problem. Give it a try. Let's see if you can do it. And you don't need a calculator for this. And I'll tell you the answer. It's 15 radians per second squared. Did you consider a free body diagram? That's probably a good place to kind of get started. And in fact, on an FRQ, they might even ask you about that. Draw the forces as they act on the object. Believe it or not, there's 2 forces that act on the object. There's an upward force here. Of course, there's also the weight acting there. The weight acts at the center of mass. And so we started with net torque equals I alpha. Good place to start. How do we calculate torque? Excellent. That's a good place to go. We need to know what those things are. Think we can work those out? What are we going to use for I? Given to you in the problem. 1/3 ml squared. Yeah, 1/3 ml squared. And we are looking for alpha. That's part of the question. So not much to do here. What's R? 50. No, I know. What is it? Probably 50 centimeters, right? Meter stick? But good call. It's a meter stick. So I'm going to put 0.5 because we do things in meters here. What's the force acting on it? What's that? I couldn't hear you. It's the weight, mg, right? And we have an angle involved here too. What's that angle going to be? Yeah, sine of 90 degrees. At the left side, we don't. I have a reason why I'm writing it, because I think some folks need to see it. Now the right side, 1/3. I'm just going to leave the m in there, because I have the m's on both sides. I noticed that. Did you notice that? I knew it was going to work out in that way, because I knew the force was going to be from gravity, so I had a feeling m's would cancel out, but, need to make sure. L's just going to be 1 squared. It was a whole thing in our last class period, what happened to the L. But it's a meter long, so just treat it like 1 meter times alpha. Now, yes, I will agree. You don't need your calculator for this. You guys are smart people. The m's do cancel. Sine of 90 is what? 1, so I don't have to worry about that either. What's G? 10. What's 10 times 0.5? So this side is 5. And this side, 1/3 alpha. You don't need a calculator. That's right. So alpha is going to be 15 radians per second squared. Now, I would strongly encourage you, when you can, to leave your calculator alone. Most of the time, you're going to have to do stuff symbolically anyways, but leave your calculator alone. It only tends to distract you. And worse, it tends to lie to you because you tell it bad information. I've called more than one of you up to my desk before to show you something you've done that's silly. It usually comes back to your calculator. Follow-up question, ready? You guys have seen the kind of the flow of FRQ. If you'll recall, one of the things they talk about in questions like this is functional dependence. So our question is, as the meter stick swings downwards, does the acceleration of the meter stick increase, decrease, or stay the same? And you have to justify your answer. Stop jumping at an answer. Start looking at the things that will influence the acceleration. You have it in front of you. Your justification has to address the things that stay the same, address the things that change, and then address the functional dependence. And what they mean by that is something that's changing. Is it causing an increase or a decrease, and why? But if nothing is changing, then something stays the same. But again, look at the things that influence the acceleration. Now take a minute, choose your checkbox, and maybe write down a sentence or two. This is our practice. We're practicing an FRQ. I want you to consider what's changing and what's staying the same based on my picture. Because after a moment or so, won't the bar look something like that? Okay. So with the bar looking something like that, we can just get this out of the way. I think we can draw the pivot point, same place. And the weight acting still at the middle will still be downwards. So let's go through this relationship and figure out what's staying the same and what's changing. All right? And what's R? Yeah, it's the distance from the pivot point to, in this case, where the force is applied. That's the center of mass. Did it change? Is R getting bigger or smaller? Is the force acting in a different place? No, so it stays the same. I'm going to underline the stuff that stays the same in white and the stuff that changes in red, okay? What is F? Force. In this problem, what does it represent? The weight. Does the weight of the meter stick change? No. All right. The angle. What is the angle here? What are we talking about when we say angle? It was 90 degrees here. Is it still 90 degrees? No, it's this angle here. So is it increasing, decreasing, or staying the same? Or is it changing at all? It's changing. So I'm going to put a red underline there to make sure we know it's changing. All right, going on to the other side, is the M changing? Is the mass of the meter stick changing? Is the length of the meter stick changing? Okay, so we have one thing that's changing. Do you guys see that? Just one. And it's the angle. Is the angle getting bigger or smaller?
I guess.
It depends on whether you measure it on that side or you measure it on this side, I guess. But is it the actual angle that matters or what we're doing to the angle? We're taking the sine of the angle. That's what determines it. Now here's my real question. We were at 90 degrees. What is the sine of 90 degrees? Can the sine function ever be greater than 1? I'm not trying to trick you. And I know you guys get this wrong a lot because your math skills when it comes to trig are sometimes dubious. But the largest value any trig function can ever be, the largest value any sine or cosine can ever be is 1. That's when it's at its maximum. Remember, it does this thing. You guys saw those pictures like that? The biggest it can be is 1. So it could be -1 or 1. So the real question is, if it's already at its biggest thing here, is it going to be at its biggest thing here? No. It's going to get smaller. 90 degrees represents when it's at its maximum. So if the angle's getting bigger, sine is still getting smaller. And if the angle's getting smaller, sine is getting smaller. So it doesn't matter which side you measure that on. The sine of that angle is getting smaller the whole time. And if the sine of the angle is getting smaller, what's happening to alpha? Is alpha getting bigger or smaller? You got to look at the functional dependence. I see sine of the angle right here. if this number is getting smaller and everything else is staying the same, that means this number has to get smaller. Right? There's no other way around it. You guys following okay? Now, here's the issue, folks. Whenever you have a justification, and we've read these justifications in class, and we've talked about how to issue points. Have you noticed the points tend to be 3 points? 1 point for choosing the correct blank, and then 1 point for what you say. Now, almost every single time, like right now, all the people said it increases, probably in trouble. It's hard to justify that because nothing here increased. You could say the angle increased, but the sign of the angle didn't increase. So the other side of this is, will you address in your answer the things that stayed the same? You have to say which things didn't change. So you'd have to say the torque arm didn't change, the force on the meter stick didn't change, the size of the meter stick and its inertia didn't change. And then you have to address what did change and how it affected the answer. The angle's changing, and therefore the sign of the angle is changing, and therefore alpha is changing. You have to address both what changes and what doesn't change. That's worth 3 points, and those are 3 points I want you to be able to get. I think you can get most of them most of the time. But again, how many of you started to think about your checkbox by looking here? Or how many of you just tried to figure it out? Yeah. I would draw pictures, because I think pictures help. Even on the test, just little diagrams, just little things. All right, you ready to move on to the next part? Turn the page over, because we're going to the next part of the FRQ. I'm just joking, the fictitious page in my head of what this FRQ looks like. But I've seen this FRQ. I could print it out for you so you could see it. So you go to the next page, because it says continue on next page. And it asks another question. It says, how fast is the meter stick going when it passes through its lowest position? So if you're writing these down, I will say all that over again. How fast, what is the angular speed of the meter stick when it passes through its lowest position? So I'm going to take the meter stick and I'm going to turn it so it's at its lowest position. When it's at its lowest position, it's got some angular speed. The question is, what is the angular speed when it makes it through its lowest position? Now, we were talking about this quite a bit in sixth period, and I want to kind of reiterate it now. The answer. So when you have a question about velocity, you should look not to forces, you should look to energy. Now, to deal with conservation of energy, this problem we haven't done before, so I'm going to kind of help you out. But remember, an object has gravitational potential energy under certain conditions. It has elastic potential energy under certain conditions. It has rotational kinetic energy under certain conditions, and it has translational kinetic energy under certain conditions. So you have to remember what those conditions are. For elastic potential energy, it has to interact with the spring or something elastic. For gravitational potential energy, its center of mass has to change height. For rotational kinetic energy, it has to be spinning. And for translational kinetic energy, remember I gave you 2 things yesterday that I said you should write down. 2 specific things that have to be true for an object to have translational kinetic energy. That's right. So, does this object ever have gravitational potential energy? Yeah, I think so. Does its center of mass change height? If this is position 1 and this is position 2, where's its center of mass at position 1? I'll give you a hint. There's a white circle around it. Where is the center of mass at position 2? Is the middle at the same height as it was at before? No. The middle is here, right? The center of mass swung downwards to here. Did the center of mass change height? It did. Because the center of mass changed height, this object had potential energy. I'm drawing a red line in here to represent the lowest position of the center of mass, which means that at position 1, the center of mass was this high above the reference level. Remember we talked about gravitational potential energy first semester, and it's about changes in height relative to a reference level. And I said in any one of these problems, you should make the reference level the lowest position the center of mass can make it to. And back then I would have said object, but now we know more about objects. We talk about the center of mass, also known as the center of gravity for just this reason. Now, when it makes it to the bottom, we have two possible kinetic energies. Does it have either or both of these? Is it rotating at that bottom position? Oh, contraire. This is it, and it's going down there. Is it spinning about a pivot point at the lowest position? Oh, it has rotational kinetic energy. There's no doubt. Does it have translational kinetic energy? Well, let's look at our definition. Emery, say it again. Okay, so that did happen. The center of mass changed location. First condition is fulfilled. What's the second condition? Wait, this has a fixed pivot point. So it has a fixed pivot point. Because it has a fixed pivot point, can it have translational kinetic energy? Nope. All right, so now we've learned something new today. We have a situation in which we have only rotational kinetic energy, even though the center of mass is moving. That's going to happen. But now we've seen it. We've seen an example of it. So now I think we can move on, right? We have this amount of energy at the start, this amount of energy afterwards. I think we can set these two things equal to each other and figure out how fast it's going. How do we calculate rotational kinetic energy? That was yesterday's topic. Do you have it in your notes? Do you remember how to do it? It probably starts with the 1/2. What's after that? What's that? Can't be m, because that would be translational. But what do you think we would use for m for stuff that rotates? What's that? We use inertia. That's right, I. And we're probably not going to use v. What are we going to use for stuff that rotates? That's right, the w thing, omega. Okay, there you go. Can you do the rest of it now? Yeah, you can. Don't say that. We're going to set those two things equal to each other. 1/2 I omega squared equals mgh. Again, we don't need a calculator for this. We're smart people. No, you don't. Try. I think you can do it. What do you mean you're not ready? 1/2. What are we going to put in for I? 1/3 ml squared. Excellent. And we'll have omega squared there. And then mgh. Okay. I think we've got some stuff in here. Let's see what we do know. First, do you notice we can get rid of those m's? M's are gone. Yep, m's are gone. What's h going to be? No. Give me, what's the number? Can't be 1 meter. For all the stuff we just talked about, Aiden, come on. Where's the center of mass moving to? This is 1 meter. So it's, remember, the center of mass is going from here down to here. So this is the new change in height, this part here. Oh, you got to be kidding me. I'm going to break out my hammer again. So, no, it's just going to be 0.5. The center of mass of the meter stick went from the height above there to where its center is. So, man. And then 1/2 times 1/3 is what? 6. What's L squared? 1. That's right, because it's just 1 squared. What's G? What's 10 times 0.5? What's omega squared going to be? If the right side is 5 and we have 1/6 omega squared equals 5, what are you going to do with that 6 here? So what's going to be on the right side? Now, I know you guys want to jump to your calculator now. Like, now it's okay to use your calculator to ask for the square root. No. What is the square root of 30? Guess. You will guess right. What's 5 squared? 5 squared is 25. What is 6 squared?
36.
Something in the middle. How close are we, you think, if we just guessed right there? We'll find out. Let's find out exactly how close we are. 30 square root 5.477. Guys, your calculator, it's not that it lies to you, it's that you guys give it bad information and you have no idea whether the answer is right or wrong. This was not hard math to do. The numbers they tend to give you on the AP exam are like this. Consider not using your calculator and then at the end check your work. You'll probably be doing better. I have one more question and we're not done. Oh, come on, there's 3 minutes. Actually, I had 2 more questions, but we won't have time for both of them. So my last question is pretty straightforward. We have the angular speed of the meter stick when it's at its lowest position. But what I'd really like to know is how fast is the very bottom of the meter stick going? What's the linear speed of the bottom of the meter stick? I need you to know how to do it. In fact, you should be able to find me the speed of any point on the meter stick. Now, if you don't know how to do this one, your notes aren't helping you then. But I'm asking for a linear speed, and I have an angular speed. Is there anything that we've talked about that could go from an angular speed to a linear speed? There is the bridging equations. You have bridging equations that bridge from linear to angular. It's not hard. You just have to multiply by the radius. So if I asked how fast the center of mass was going, you'd multiply by 0.5 meters. If I asked how fast the edge was going, you'd multiply by what? 1. So the answer is going to be 5.5 meters. Yep. If you didn't know those things, you should be writing them down, actively trying to make sure you are better tomorrow than today.